Hello. In this video and the next, we are going to finally introduce the first and second laws of thermodynamics. Before we do that though, let's remind ourselves of the main ideas that we have covered in the previous videos. What I have tried to do in these videos is to explain the distinction between extensive and intensive thermodynamic variables. The very first time these ideas were introduced, I explained how intensive thermodynamic variables do not depend on the number of atoms in the system, and how extensive variables do depend on the number of atoms in the system. In subsequent videos, I have tried to refine these definitions, and I have explained how extensive thermodynamic variables are a property of the system's state. The extensive thermodynamic variables define the state of the system. Intensive thermodynamic variables, by contrast, tell us something about the way that the system interacts with its surroundings. I like to talk about this distinction in this way because a key realization is that if the intensive thermodynamic variables in two phases that are in contact are different, then those two phases will exchange the conjugate extensive thermodynamic variable. Another of the key things that we have learned about intensive and extensive thermodynamic variables is illustrated on this slide. In the diagram here, I'm considering the various states that a one-component, one-phase system can adopt. In accordance with Gibbs' phase rule, I need two thermodynamic variables to define the state of this system. I have chosen the volume and the entropy as these two variables are both extensive. I now want to consider the work done on the system as it changes state. I will start by considering changes in state that only involve changes in the volume of the system. In other words, during these changes I'm currently considering, the entropy will be kept fixed. These will be adiabatic transitions. In my video on the work in the Carnot cycle, we learned that for these sorts of transitions, the total work done by the universe on the system is given by this integral. The negative sign here implies that as the system's volume increases, it must do work on the universe. During these transitions, no heat is output from the system or input into the system. The transition shown here is thus adiabatic. Only work is input or output from the system. In the last of the videos on the Carnot cycle, I alluded to an equation that is similar to this that holds when you have transitions that involve the transfer of heat only. That is to say, transitions like this one shown here, in which the entropy changes but the volume does not. In any transition like this, where only the entropy of the system changes, only heat is transferred, no work is done. We can write the heat output in a transition such as this one using the integral shown here. We call transitions, such as this one, isochoric, which is a word we use to refer to transitions during which the volume does not change. The aim of this video is to discuss transitions such as this one here, in which the volume and the entropy of the system both change at once. Now at the moment, we only know how to calculate the heat and work output when we have transitions that run parallel to the volume and entropy axes on our graph. This is different to what we had in Newtonian physics, where we could think about the changes of state caused by an external agent in terms of what effects such stimuli have on the momentum of the system. In thermodynamics, by contrast, we currently have to think about two types of perturbation that an external agent can make to our system. The first of these is that the universe can heat up the system. The second is that the universe can do work on the system. Keeping track of both these types of perturbation is a pain, especially if we have transitions in which the universe injects heat and work into the system at the same time. What we would thus like to do is to define one single quantity that characterizes the various ways that the universe can perturb the state of the system. With this objective in mind, we introduce the concept of internal energy, and we write the change in internal energy, delta E, as the sum of the heat introduced, delta Q, and the work done on the system, delta W. Thinking about the isochoric and adiabatic transitions discussed earlier, we can come to some realizations about the changes in internal energy that accompany various types of transition. If our transition is adiabatic and only the volume is changed, that is to say, if the entropy is fixed and the transition is adiabatic, the change in internal energy is equal to the work done on or by the system, as no heat is transferred. Now we know how to, if by contrast the transition is isochoric, so that only the entropy changes but the volume stays fixed, then the change in the total energy is equal to the heat input or output from the system, as no work will be done. Now we know how to calculate both these quantities, so we can write the following two results. Where we have introduced the symbols delta E underscore S to indicate the change in internal energy if the entropy is held fixed during the transition, and the symbol delta E underscore V to indicate the change in internal energy that occurs for a transition in which the volume is held fixed during the transition. We can use these formulae to arrive at an appealing definition of the intensive thermodynamic variables P and T. Remembering that integration is the reverse of differentiation allows us to write that the integrands in these two expressions, the minus P and the T, are equal to partial derivatives. Hence, minus P is equal to the partial derivative of E, the internal energy, with respect to V, the volume, at constant S. We use the small s next to the partial derivative here to indicate that we are keeping S, the entropy, fixed when we take this partial derivative. Similarly, the partial derivative of the internal energy with respect to the entropy at constant volume is equal to the temperature. This brings us nicely to the first law of thermodynamics, which states that the internal energy is a function of state. That is to say, the internal energy depends only on the state you are in. We can express this requirement by requiring that the integral of the internal energy, if we go around a closed path, is equal to 0. This assumption puts us in a position where we can now state what the change in internal energy is for transitions such as the one shown here. The fact that the integral around a closed path is equal to 0 means that the change in internal energy depends only on the initial and final points for our integral. I discussed this at length in my video on Newton's third law. In other words, the value of the integral does not depend on the path that I take between these initial and final states. I can thus calculate the change in energy as I move between these two states as follows. I first integrate along a line parallel to the volume axis, as I know how to do this integral. I then integrate along a line parallel to the entropy axis, which is also an integral I know how to do. I thus find that the change in internal energy as I move between the two states shown here is given by the expression shown here. Remember that the value of this quantity does not depend on the path taken, because the first law of thermodynamics tells me that the internal energy is a state function, and hence that the change in internal energy that takes place in moving from initial state A to final state B depends only on state A and state B. It does not depend on the path taken between these two states. The first law of thermodynamics is extremely important, so important in fact that we have already reused it. If you remember in my first video on the Carnot cycle, when I was deriving the expression for the efficiency of this type of engine, I stated that if I added together the heat absorbed from the bath, QH, the heat emitted to the sink, QC, and the difference between the work done by the engine as the gas inside it expanded and the work that was required to contract the gas of the engine, I got 0. The reason that I am able to do this for this engine is that when a full cycle of the Carnot engine is completed, the system returns to its initial state. The first law thus tells us that the net change in internal energy on completion of a loop around this circular path is equal to 0. In other words, this quantity, QH minus QC minus delta W, is just equal to the change in internal energy, which, by the first law, is equal to 0. To summarize then, we have arrived at the following definition of the change in internal energy that takes place during a transition, and have also arrived at the first law of thermodynamics. The change in the internal energy of the system that takes place during any transition is equal to the sum of the work done on the system during the transition and the heat input into the system during the transition. This quantity is useful because the first law of thermodynamics tells us that the internal energy is a function of state. In short, if we move around a circular path that starts and ends in the same thermodynamic state, the internal energy of the system will return to its original value. Consequently, the change in internal energy that occurs as we move from state A to state B does not depend on the path that is taken. That's all for now, so thank you for your attention.